In this video, we're going to introduce the basic form of an exponential function. So in general, exponential functions such as this one, f of t, they'll be written as a times b to the t. And sometimes you'll see this also written in this fashion. A times b to the t, where the b is written in parentheses. But these are two important values, a and b. They drive the function. This first value, a, is the initial value. It's the output you would get if you put in 0 for t. It's also the vertical intercept. B is the growth factor. If b is a number greater than 1, meaning you're multiplying by a number larger than 1 over and over and over again, you'll get growth. If b is a number less than 1, you'll get decay. The larger the value of b is, the faster the function will grow, assuming it's greater than 1. The smaller a number is, b, assuming it's less than 1, the faster the function will actually decay or decrease. So let's look at how to apply these ideas. Here we're given 4 different functions, and we want to answer some questions about them. First, which functions are increasing and which one's increasing the fastest? Since a of x and c of x both have growth factors, this b value, greater than 1, those are the functions that are going to be increasing. So a of x and c of x are increasing. Since c of x has a growth factor of 1.35, which is greater than the growth factor of 1.25 for a of x, c of x is increasing the fastest. The other two functions are decreasing. Notice how this value of b is less than 1, 0.85 and 0.91. So b of x and d of x are both decreasing. Here, since 0.85 is the smallest number, multiplying by 0.85 over and over and over again is going to cause the function to decrease at a faster rate than multiplying by 0.91. So in this case, b of x is decreasing the fastest. The front value, the a value, is the initial value. So the function that has the largest initial value is going to be b of x. It has an initial value of 110. The function that has the smallest initial value is a of x because it has an initial value of 90. So let's apply these ideas to graphs. The initial value, a, if we're considering these as f of x equals a times b to the x, will help us get a good start. So let's try and identify this f of x equals 3.25 times 1.21 to the x. This is the initial value, 3.25. If I look at this graph, the black graph, C, has an initial value of about 3.25. That's where it intersects the vertical axis, and it's growing. So I would assume that this is C. The next function, you'll notice, has an initial value of 4.7. And there's another one that also has an initial value of 4.7. I assume that these two graphs, these have a vertical intercept near 4.7, graph B and graph E. Notice how graph B is increasing and graph E is decreasing. This one must be graph B because it has a vertical intercept of 4.7 and is increasing. The 1.12 tells me that's increasing. Graph E must be this one. It has an initial value, a vertical intercept of 4.7, but is decreasing. That gets us to our last two available functions, and you'll notice both of them have a vertical intercept of 2.5. But you'll notice the graph of A is increasing much faster than the graph of D. Since this function has a larger growth factor at 1.36, I would assume that would be A, and this one must be D.